In the previous video, we have successfully implemented the push functionality, which will basically add the new value at the end of the singly linked list, right? In this video, let's try to perform an operation which will basically delete the very last node we have inside the singly linked list. So that operation is nothing but pop operation. So we already know the very last node is nothing but the tail node we have inside the singly linked list, right? And we have to delete that node from the singly linked list. That basically means that inside the singly linked list representation that we are maintaining, right, we are maintaining the head node and tail node. Along with that, we are also maintaining the length of the singly linked list. So we have to make sure that we are making proper adjustments in these three variables according to the cases that we are seeing. Here, one thing that you have to remember is basically deletion doesn't mean that we are actually freeing up the memory. So what exactly we mean by deletion is in the case of singly linked list, right, every node will have the reference of the next node, right? That means if you take the reference of the node true, it will be available inside the node with the value code. Similarly, the reference of the code will be available on the node 10. Similarly, the very last node we have inside the singly linked list is false, right? And this reference will be available inside the node -10. So to delete the node false, that is the very last node we have inside the singly linked list, what exactly we will do is the next that we have inside the node -10, that we will update it with null. In the case of Python, we will update it to none. Okay, so in that way we are losing the track of the very last node because we have deleted the reference. That means that that node is no longer available inside the singly linked list. And remember that since we are deleting the very last node, whatever the tail node that we had previously will no longer be the tail node. We have to update the last but 1th node as the new tail node of the singly linked list. Okay, so that is a simple way how we actually delete a value inside the singly linked list. What exactly are the different cases that could appear when we are trying to perform the pop operation? Let's assume that user is trying to perform the pop operation on a empty singly linked list. That means that there are no nodes at all inside the singly linked list. That means both head and tail are empty and length is 0. In that case, obviously, since we don't have any values, we will not be able to perform pop operation. In that case, we will simply return null, and if we are following Python based representation, we will simply return none. Okay, so that is the first case. In the second case, where we have only one node inside the singly linked list, in that case, since we have only one node in the singly linked list, right, let's assume that only one node is 10. So obviously head will be pointing to this node and we will also have the tail at the same node, right? So the only node is available inside the singly linked list and we have to delete that only one node, because as part of the pop operation what we do, we will delete the very last node. When we have the only one node inside the singly linked list, pop operation, we will have to delete that only one node. In that case, since we are deleting this, the singly linked list will become empty. So how will we exactly represent an empty singly linked list? To represent that, head we will update it to null or none. In the case of Python, we use none. Similarly, the tail also we will update it to the similar way how we have updated in the case of head. And there are no values inside the singly linked list at all, right? In that case, we will simply update the length to 0. So in that way, we are making sure that there is no inconsistencies in the head or tail or length that we are maintaining for representation of a singly linked list in our implementation. And the third scenario is obviously we have more than one node. So if we have more than one node, this is the classic example, right? So in that case, head will be somewhere and tail node will be somewhere. So we have to make sure that we are deleting the very last node. So how will we actually delete is, let's take a small example where we have, let's say, 3 nodes available inside the singly linked list. So this is the head node and this is the tail node, and let's assume that 10 code and true are the values present inside the singly linked list. So according to the algorithm that I have explained, how will we delete the last node? We will simply go to last but 1th node, that is we will go to the node code, and there we have the reference of the true inside that node, right? And we will simply assign it to null or none based on the choice of the programming language that we are using. Okay, so as part of the first step, our aim is to reach the last but 1th node, and there we will update the next to null, and whatever the node that we have deleted, right, in that way we are losing the reference of the node true. So the connection has been removed, as a result the value has been lost from the singly linked list. But the thing is, the tail is still available at true only, so and that is not part of the singly linked list. So we have to make sure that last but 1th node is becoming the tail node. That's why in the case where we have more than one node, we will go to the last but 1th node. There we will update that nodes next to null or none based on the choice of the programming language that we are using, and we will basically decrement the length by 1 because we are deleting the node after all from the singly linked list, and we have to make sure that the tail node is getting updated to last but 1th node. Okay, so that is the process of performing a pop operation on a singly linked list. I hope you understood. Now let's write the pseudocode for the same. So to write the pseudocode, obviously first what we will do is we will write a function called pop function. Obviously it will not take any argument, and it will basically delete the very last node, and it will return that node back to the user. So as part of the first step, what we will do, we will check if the singly linked list is empty. If it is empty, what we will do, we will simply return null or none based on the choice of the programming language that we are using. So this is the case where we have the singly linked list is empty. The second case is where we have only one node. That means if the length of the singly linked list is 1, that means whatever the length variable that we are maintaining, right, if the value inside that is 1, the singly linked list has only one value. Besides this, one more comparison that you can do for checking if the singly linked list has only one value or not is because when we have only one node inside the singly linked list, head will be at the same node and the tail will also be at the same node. So you can simply do head is equal to the tail as well to check if the singly linked list has only one value or not. If at all, if that condition is matching, how we will delete the last node? We will simply update the head that we are maintaining. We will simply update it to null or none based on our programming language of choice for implementation, and inside the tail that we are maintaining, we will also make it as null or none, and the length will become 0 because there are no nodes inside the singly linked list after deleting. But in the end we have to return the node that we have deleted, right? But that's why before performing or updating the head to tail to none, just read the tail node, okay, and store it in some variable. In the end, return that old tail. Okay, so that is the case where we have only one value inside the singly linked list. Now let's just try to perform the pop operation on a singly linked list where we have more than one node. So otherwise, so the logic will be simply otherwise. That means that we haven't matched the first two cases. That means that we have more than one node inside the singly linked list. So in that case, what we will do, we will go to last but 1th node. So first process is to check read the last but 1th node. So we will start at the head node and we will keep track of the previous variable, and using that previous variable we will go to the last but one node. Once we go to that node, right, how will we delete the last node? We have the reference of that node in the last but one node, right? That is available in the next of the last but one node. So we will update next to, we will simply update it to null or none based on our programming choice of implementation, and we will simply update tail to last but one node, because the reference of this node has been lost in the last but one node because we have updated it to null or none. So this will no longer be the tail node. So we have to make sure that tail node is getting updated to the actual tail node or the very last node we have in the single linked list, which is nothing but the last but one node. And here we will again decrement length by 1, because after all we are deleting one value from the single linked list, right? So since that value has been deleted, we have to make sure that we are making proper adjustments in length as well. Since we are deleting one node, we will decrement the length also by 1. In the end, just like how we read the tail node, we will first read the tail node here in this case as well, so that in the end we can return the old tail of singly linked list, which is actually getting deleted from the singly linked list as part of the pop operation. So this is the pseudocode for implementing the pop operation on a singly linked list. So just remember that there will be 3 cases. First case will be empty singly linked list, and the second case will be where we have only one node inside the singly linked list, and the third case is where we have more than one node. So according to that case, we are handling and we are making sure that head, tail and length which we are maintaining in our singly linked list in presentation are getting adjusted with the proper values. So here let me just define the function which will basically return the node that we are deleting. Basically pop operation deletes the very last node, right? After deleting that node, we need to return that back to the user, whoever is calling this specific function. So the return type of the function will be node, and the name of the function is pop, and this will not take any arguments here. Now here we need to write the logic honoring 3 cases, right? Whenever we are removing the value from the singly linked list, there are 3 scenarios. One is the singly linked list is empty and the singly linked list has only one value, and the singly linked list has more than one value. We need to honor the logic covering these 3 scenarios. But first anyway, as we are deleting the tail node and we need to return that node back to the user, right? So what we can do is first let's read the tail node as we have the access of it, so that in the end we can return that. So let me read the tail node, this dot tail. Okay, it's just that in the end we will have this value handy so that we can return it. Now we need to write the logic for honoring 3 cases. First scenario is obviously the singly linked list is empty. If the singly linked list is empty, we can't do anything, right? So how we will check if the singly linked list is empty? We can do that by depending upon the head and tail value, which is null if the singly linked list is empty, or we can rely on the length of the singly linked list. It will be equal to 0. So based on that, we will be able to say if the singly linked list is empty or not. Obviously, if it is empty, there is no tail value, right? Head and tail are not there. Obviously, there is no node that we can delete. So we can simply return the null value itself, which is nothing but this tail node that we have read itself. So here we can simply do return tail node. Okay. Otherwise, what you can do is you can return null like this as well, which is both of them are absolutely fine. If this is not the case, then first case that we have handled is if the singly linked list is empty. Obviously the next case is when the singly linked list has only one node. Obviously when we have only one node, both head and tail will be pointing to the same node. So what we can do, we can compare if head equal to tail, that we can do. Otherwise we can also rely on the length of the singly linked list. So this dot length is equal to 1, that means that singly linked list has only one value, and that one value itself we are deleting. That means since that is the only value, it is the head node and it is the tail node. As we are deleting the only tail node that we have as part of this pop operation, both head and tail will become empty. So here what we will do is, whatever the head that we are keeping track of on the singly linked list, this we will initialize it with null, and whatever the tail that we have, we are going to initialize it with null. Since the only node that got deleted, the length of the singly linked list should be equal to 0. Okay, and after this we need to return the node that we have deleted, which is nothing but the tail node. Since we have it here, we can do simply return tail node like this. Okay, so we have handled the second scenario also perfectly fine. Now comes the third and important scenario we have. Now, as part of the third scenario, we have more than one node in the singly linked list. Now, if we delete the very last node, whatever the tail variable that we are keeping track inside the singly linked list, right? If we simply modify the tail value, whatever the last value that we have, the previous value of the current tail node will be the last node in the modified singly linked list. So we need to make that node as a tail node of the singly linked list. For doing that, since it is a singly linked list, we will be able to go to the next node only. So first we need to reach that specific last but one node, such that we can make that as a tail node of the singly linked list. For that, what we will do is, let's just write the logic for that. And let me just define one variable called current node. Since we need to start our journey of going to last but one node from head node, right? So I've defined one variable called current node and I've updated with head. Now let me just define one more variable. Let me just say this is the new tail. Here ultimately, after completing our logic, this new tail will have the reference of the last but one node, which we can make it as a tail of the singly linked list. And this also, let's just assign it with the head node in the beginning. Okay, now what I will do is, I will simply run a loop as long as whatever the current node that I am processing, if the next of this is not equal to null, till that point of time I want to run this logic. In this logic, what I want to do is, I simply want to update the new tail to whatever the current node that I am processing. Once I am done with updating this, I will simply move on to the next node, such that this logic will continue. Once we reach the tail node, right? Tail node dot next will be equal to null. As a result, we will break out of this loop and this new tail will be pointing to last but one node. So here we need to move on to the next node. So let's just update the current node to current node dot next. Okay, once we are done in this loop, this new tail variable will be pointing to the last but one node. So to delete the existing tail node, what we need to do, in this new tail dot next should be updated to null, and this new tail will be the modified tail of the singly linked list. For that, let me just make new tail dot next is equal to null. By doing so, whatever the last node that we have, we are deleting that. Now this new tail is the very last value we have in the modified singly linked list. As a result, let's just make this dot tail is equal to new tail. Okay, as we have deleted one value from the singly linked list, the length should be decremented by 1. So this dot length is equal to this dot length minus 1. Okay, so that is the logic. Anyway, here also after deleting, we need to return the node that we have deleted, which is nothing but this tail node. So we can simply return that also here. Okay, if you see this function, right, ultimately what we can do is, we can eliminate all these return statements here and we can write the common return statements here directly, return tail node. That is also absolutely fine. It's just that I want to explain each and every case thoroughly so that we will have better clarity. That's the reason why I'm approaching the function implementation this way. Okay, anyway, that is the pop operation implementation. Okay, now let's just try to call the pop operation on the singly linked list. And here let me just comment out printing of the head nodes, tail nodes and all those things, because anyway we have understood that, right? And let me just comment out the second singly linked list as well. As we understand the things on this singly linked list of type integer, you can replicate the same on the singly linked list of type string as well. Okay, here after traverse, let me just do SLL dot pop, and after pop let me just do the traverse. Okay, now on the singly linked list we have the three values. So the tail is -10. So if we perform the pop operation, this -10 should be deleted, and in the modified singly linked list 0 and 10 should be there. Head should be at 0 and the tail should be at 10. So if we execute this program, that is what we should see on the console. Okay, seems like I haven't put some comma and arrow based representation I need to use here. I can simply do the next and semicolon. Where did I miss it? Line number 62 here. Okay, so anyway, let's just try rerunning the code. Okay, if you see here, before performing the pop operation, these three are the values, and after performing the pop operation only two values are left. If at all, if we want to perform the pop operation once again on the resulting singly linked list, as part of the first pop operation we have deleted this one. As part of the next pop operation, the modified singly linked list tail is 10, right? That also we will delete as part of the second pop call. As a result, if we try to perform the traverse after the second pop as well, you should be able to see the only 0 on the resulting singly linked list. So if I execute this, see, before performing the pop there are three values, after performing the first pop there are two values, and after performing the second pop there is only one value. If at all, if we perform the pop operation once again, the singly linked list will become empty, because whatever the only one node that we have, that also we are deleting. So as part of the second traverse you should not see anything. See, it is a blank line here. Okay, so in this way we will implement the pop operation on a singly linked list, honoring all the scenarios. Alright, now we have already implemented the pop operation as well, right? In this video, let's try to understand time and space complexities involved in the pop operation. So obviously, let's just try to divide it into best case as well as the worst case scenarios for both space and time complexities. So when will the best case of pop operation will actually occur? When the singly linked list is empty or it has only one node inside the singly linked list, because we don't have to go to last but one node inside the singly linked list, right? That's why the best case will occur at when we have only one node in the singly linked list or empty single. In that case, what exactly we are doing? In the case of empty, we are simply returning null or none based on our programming language of choice. In the case of when we have only one node, we are updating the head node with the null or none and tail node with the null or none, and length also we are decrementing by 1, or we are making it to 0. So obviously all these operations are simple assignment operations, right? And these assignment operations will take 1 unit of time. As a result, in the best case scenario, the time complexity will be order of 1. Okay, now let's talk about the worst case scenario. Let's assume that the singly linked list is that we have, on which we are trying to perform the pop operation, is something that like you see on the screen, where let's just assume that we have n number of nodes, right? In that case, what exactly we are doing? We are going to last but one node. That means we have to start at the head node and we have to go to last but one node. That means that we have to run a loop for going till the last but one node. That loop we are running it for n minus 1 number of times, right? So in that case, once we go to that node, we are updating the next appropriately so that the last node is getting last. and after that we are updating the tail to null or none. So obviously the overall time complexity in the worst case where we have n number of nodes, the major operation is to go till last but one node. For that we are running a loop and it is running n minus 1 number of times. As a result, we can say the time complexity will be order of n minus 1, which is nothing but order of n as a worst case time complexity for pop operation. Okay, so that is something that in terms of time. So let's talk about in terms of space. So we already have the head and tail and length inside our singly linked list representation. So in the best case scenario, when we don't have any values at all, or when we have only one value, we are simply updating the head with null or none, and similarly tail also getting updated with null or none, and length we are updating it with 0. And these are simple assignment operations, right? And obviously assignment operations will not take more than unit amount of memory internally. As a result, in the best case, the time space complexity will be order of 1 only. Okay, now in terms of worst case space complexity, yeah, we are sure that we are running a loop for n minus 1 number of times, but we are taking a help of a single variable for keeping track till the last but 1th node. We are simply using a single variable, and that variable itself is keeping track of the previous node. In that way we are going to last but 1th node. Obviously, since it is a single variable, it will take constant amount of memory, and after that the tail node is getting updated to last but 1th node, and length is also getting decremented by 1. These assignment operations will obviously take constant amount of memory only. As a result, the overall space complexity in the worst case also, where we have more than one node, or where we have n number of nodes inside the singly linked list, even though we are running a loop for n minus 1 number of times, the space complexity will still remain constant only, because we are simply using a single variable for going till the last but 1th node. Okay, so that is the space complexity in the worst case scenario for performing the pop operation on a singly linked list. Okay, so that is how we calculate the time and space complexities, and that is how we exactly implement the pop operation for various cases that can come while implementing. Okay, in the next video we will get on with implementing the next functionality on a singly linked list. Okay, I'll see you there.